Hello everyone, thank you for signing in and watching my live stream. I'm Mr. Matt and this is Dr. Tot. You want a cookie, Dr. Tot? Yes. And welcome to Geometry. We're going to continue our discussion today with proofs using triangle congruency postulates. First we're going to talk about just a few properties and concepts, vocab that are going to be relevant throughout your proofs with triangle geometry and especially with today's lesson. And then we're also going to review the 4 postulates that concern triangle congruency, and then get into some actual proofs. So let me share my screen with you. And just a reminder, these are live sessions, so there's a little bit of a delay with the iPad, but I'll keep track of that. If you have any questions at any point, just post them in the live chat feed, or you can comment if you're watching the recording below. But first off, let's talk about a few concepts that are going to be really important in our proofs. First off, the reflexive property of congruence. So the reflexive property just merely says anytime that something shares a side or shares an angle, that something is always equal to itself. So that particularly comes up, like for example, if we had a shape like this, so in the first diagram that I drew, you can obviously see that the 2 triangles share this side AB because it makes up that four-sided quadrilateral. So we could say, because due to the reflexive property of congruence, that side length AB has to be congruent to side length AB because it's the same thing. The same thing is true for this angle measure, BAC. Notice that the 2 triangles, the larger triangle, let me call this point D, the larger triangle ABC shares that angle BAC, with the smaller triangle, let me call this point E, ADE. So they both share that angle, so we could say that angle BDA is congruent to angle we could say that, let me write that out, angle DAE, I should have said, is congruent to angle BAC in the larger triangle because they share the same angle. It is the same thing. So that's what the reflexive property tells us. And that comes up all the time because if you want to use a particular postulate in order to prove a statement to be true, usually that one triangle is congruent to another triangle, then you have to explicitly state your reason for why each of the components of the postulate is true, making the overall argument true. So for example, with side angle side, you have to come up with an explicit statement and reason as to why each corresponding side, a particular set of corresponding sides are congruent, a particular set of included angles are congruent, and then another particular set of congruent sides, of corresponding sides, are congruent, in order to prove ultimately side angle side congruency and that the 2 triangles overall are congruent. So it's really important in geometric proofs that each statement is explicitly reasoned out and not just implied. So it might seem too easy, or it might seem as if it's not necessary to write out that something is equal to itself, but you have to use you have to provide a logical reason for each of your statements in order to prove each of the components to be true so that the overall argument is proven to be true. If you have any questions about that, just let me know. The second thing I wanted to talk about is the vocab word bisect, the verb bisect, or the noun bisector, or bisector, however you want to pronunciate that. So something that a bisector bisects something else. So it could bisect an angle, or it could bisect another side. If it bisects something else, that means that something else is split into 2 congruent parts. So if in this diagram here, this red triangle ABC, if we say that side length or line segment CD bisects angle ACB, then we know that the resulting component angles, the resulting angles of that split have to be congruent to each other. So angle ACD has to be congruent to angle BCD. And we could use that in our proofs to prove that these two triangles are congruent. Similarly, a midpoint is a point on a line segment where the two resulting components or the two resulting segments must be congruent to each other. So in this diagram, we have line segment AC. If I tell you that B is the midpoint of line segment AC, then you can conclude that line segment AB must be congruent to line segment BC. Definition of a midpoint. The next idea or concept is really going to come up more frequently in some latter lessons or later lessons, but I wanted to mention it now. Congruent parts of congruent triangles are congruent. That's abbreviated as CPCTC. So if you know that two triangles are congruent, then you know that their corresponding sides and corresponding angles are congruent. So this comes up when we're proving, we have proofs that are kind of stated in the reverse than we're normally used to. Normally they give us some type of information about the component parts of two sets of triangles, like two corresponding sides are congruent or two corresponding angles are congruent. Something is the bisector of another thing. One point is the midpoint of some line segment. They give us component parts in order to build up into an argument that proves the overall triangles are congruent. This concept or this reason, this logical argument allows us to work backwards. So for example, if they gave us as given information that two triangles are congruent and asked us to prove that two line segments, corresponding line segments within those triangles are congruent, we could use this postulate. That if the two triangles overall are congruent, then corresponding parts must be congruent. But again, we'll have more on that later, but that's just a little bit of food for thought. The last concept that's going to be very important, vertical angles. When two straight lines intersect, they produce two sets of congruent angles. So anytime two straight lines intersect, they're going to produce two pairs of congruent angles. The angles don't all have to equal each other. That will occur if the angles are 90 degrees. So if the lines are perpendicular to each other and they produce 90-degree angles, if one of them is 90 degrees, then all of them have to be 90 degrees because the vertical pairs tell us that this angle has to be congruent to this angle. And so that only leaves 180 out of the total 360 in this total thing. This whole thing makes up a circle, right? So we know that there's 360 degrees to split between these four angles. So if one of them is 90, its opposite vertical pair has to be 90, meaning that you've used up 180, 2 times 90. 360 minus 180 is 180, and 180 divided by 2, because they have to be equal to each other, is another 90, or each 90. So if one of them is 90, all four of them have to be 90, but that's usually not the case. Usually they're two pairs of different angles. And actually I did want to point out one other thing. Whenever you have two parallel lines intersected by another line called a transversal, they produce a whole bunch of congruency relationships. So alternate interior angles, that would be like, oops, this guy is congruent to this guy, with these angles in here that I'm marking in this kind of cranberry color. Then we also have alternate exterior angles. And they're also congruent. So for example, this guy right here is congruent to this guy over here. And same thing for these smaller angles in here. Consecutive angles are supplementary. So for example, I'm just going to draw circles. If they're supplementary, that means that they add up to 180. Okay, so if there's any questions about that, just let me know, but I wanted to give an overview. Some of those things can come up in proofs. Before we get into some actual proofs, let's review the 4 congruency postulates that are relevant to proving two triangles are the same. So the first, we have angle side angle. So if two angles and an included side of a triangle are congruent to two angles and an included side of another triangle, then the triangles are congruent to each other. So if we have two triangles like this, if I know that this angle is congruent to that angle, if I know that this angle is congruent to this angle, and the included sides are congruent, then I have angle side angle. It's really important to understand that the side has to be inside or included between the two angles. It can't be on the offset. The second postulate, we have side angle side. So very similar, just kind of the alternate form. If two sides and an included angle of a triangle are congruent to two sides and an included angle of another triangle, then the triangles are congruent to each other. So if I have two triangles, and I know that this side is congruent to this side is congruent to that side, and the included angles, I should say, are congruent, then I know that the two triangles are congruent to each other. But again, that angle has to be inside of the two congruent side pairs. If they're on the outside, if they're either one of the other two angles, then it's not included, and that's not side angle side. Next, we have angle angle side. So if two angles and a non-included side of a triangle are congruent to two angles and a non-included side of another triangle, then the triangles are congruent to each other. So if I have two triangles, so if I know that this angle is congruent to this one is congruent to this one, and then the non-included side length all the way over here are congruent, then I have side angle side. Excuse me, angle angle side. Similarly, I could switch this up, but I just need to make sure that they're in the right order. So for example, this could also be, if I know that these two angles are congruent, and then these two, so the same type of setup as before, but then the side is over here, that's also okay. You just have to make sure that they're the same sequence around the triangle for both of the triangles. If it was a mix match between these two pairs, if you had one of the blue triangles and then one of the red triangles, that would not prove angle angle side because they're not in the same sequence. So they do need to be in the same sequence going around the triangle. And then lastly, we have side, side, side. So if 3 sides of a triangle are congruent to 3 sides of another triangle, then we know that the triangles are congruent to each other. So if I know that this side is congruent to that side, this one to this one, and then lastly that one to that one, I have side, side, side. But it's important to understand that it's not this. So notice that the order matters. So if I don't have them in the same order, if they're not opposite corresponding angle measures, then this is not going to be the case. But if you're able to rotate them, actually in that case, I'm sorry, in that case we could rotate this around. I apologize. Let me make a correction here. Notice here we can rotate this guy. So if well actually, no, we'd have to flip it. No, I'm sorry, my first value was correct, or my first description. My apologies. So this is not because we can't rotate it to get the same sequence around. If we could rotate it, then stereotopically they would actually match up and they would be fine. But if we can't rotate them to get the same sequence, then that does not prove side, side, side. I'm sorry, I hope that wasn't confusing. My apologies. If you have any questions, then please let me know. Otherwise, let's take a look at a few proofs. I'm going to give you 4 minutes. Please look at this first problem, and then I'll give you the answer. I'll keep track of the time in the upper right-hand corner and update it per minute. Okay, so looking at this guy, they say that the measure of angle HFG is equal to the measure of HIJ, which is equal to 90. So they're telling us basically that these two angles are 90-degree right angles. However, it's not given to us that the two angles are congruent. We know that does mean that they are congruent, but we can't assume that in our proof. So the first statement, we could say that the measure of angle HFG is equal to the measure of angle HIJ, and that's given. So based on that, our second statement can conclude that the angle HFG is congruent to the angle HIJ because of the definition of a right angle. All right angles are congruent. And actually, I'm going to put that down here. So now we've proven that this angle is congruent to that angle. So even though that they stated that the measures are equal, notice that that's not technically the same thing as proving that they're congruent. We know logically that does mean that they're congruent, but you have to explicitly state it in order to prove that component of the overall congruency postulate. So far we have an angle proven to be congruent, a set of angles proven to be congruent. So I'm going to write an A up there. Now they tell us that side length GH is congruent to side length JH. So GH right here is congruent to JH. So side length GH is congruent to side length JH. And that's given. Now, we're just missing one other component here. So we have a side. Notice we could also make a conclusion about these two angles, because these two angles are created from the intersection of two straight lines. So we know that these two central angles are vertical pairs of one another. So we can say that for the fourth statement, we can say that angle FHG is congruent to angle IHJ because of the definition of vertical angles. So now we have angle, angle, side. That's a congruency postulate. So we can make a conclusion that triangle HFG is congruent. Ooh, that's terrible. Is congruent to triangle HIJ because of the angle, angle, side congruency postulate. If you have any questions, then please let me know. Otherwise, let's take a look at the next problem. So I'm going to give you 4 minutes. We have this diagram of the quadrilateral EFGH that's split down the middle by FH. You're given that side length EF is congruent to side length GH, and EH is congruent to side length GF. And you're asked to prove that triangle EFH is congruent to triangle GHF. So I'll give you 4 minutes, then I'll give you the solution. Okay, so they tell us that EF is congruent to GH and EH is congruent to GF. And you might be able to notice as well that they share this side of FH. So FH has to be equal to FH. So therefore, we have side, side, side congruency. So my first statement, I'm going to start with the given. Side length EF is congruent to side length GH because it's given. So that's one of the side lengths that I've just proven. It was given to me. Then EH is congruent to GF. That was also given. That's the second side. And then due to the reflexive property of congruence, I know that FH is congruent to FH. So I can say that side length FH has to be congruent to side length FH because of the reflexive property of congruence. And so I've just proven that three corresponding pairs of side lengths are congruent to each other. Therefore, the overall triangles, triangle EFH, has to be congruent to triangle GHF. And that's due to side-side-side congruency postulate. If you have any questions, then please let me know. So next, let's look at this problem. So I'm giving you the fact that line segment FG is parallel to line segment JI. So that first given statement there, FG, line segment FG, and there's two vertical lines, that means that the lines are parallel to each other. So line segment FG is parallel to line segment JI. And another way of demarcating that are these little arrow points. So that means that those two lines are parallel. So I'm going to give you 4 minutes, and then I'll give you the solution. Okay, so if they tell us that these two lines are parallel, that's going to involve, that's going to bring about a lot of relationships with the transversals that are going through these two lines. Notice that line GJ could be extended out. We could think about all of these lines as being extended out like this. And these are really the intersection of two straight lines here. But in either case, either you think about this as being the transversal, and you can draw all of the conclusions that come from a straight line intersecting two other straight lines. So either you think about FJ as the transversal, or you can think about the other line segment, GJ, as the transversal, and therefore all of those relationships would be apparent. So if you think about that guy as the transversal, then you have all of those alternate interior, alternate exterior, consecutive angles, so on and so forth. Let me back out all of these marks so it doesn't get too confusing. So if they tell us, first of all, we know that these two, let's start with the more basic stuff. We know that these two angles have to be congruent to each other because they're vertical pairs. Then they also tell us that H is the midpoint of GJ. If H is the midpoint of GJ, then GH has to be congruent to HJ, because that's the definition of a midpoint. So I'm going to start with that statement. I'm going to say that they tell me that H is the midpoint of GJ, and that was given. Therefore, from that statement, we can conclude that line segment GH has to be congruent to line segment HJ because of the definition of a midpoint. So we've just proven one pair of sides to be congruent. I'm going to move on now, and I'm sorry, there is a little bit of a delay with the iPad, so bear with me. I was just pausing for a second to let it catch up here. So we've proven one pair of sides to be congruent. Now I'm going to move on to the fact that line segment FG is parallel to line segment JI, and that's just given. But now I'm going to choose to talk about these two angles being parallel. These two angles being congruent. So I'm talking about angle FGH and IJH. I'm picking those angles rather than the other pair of angles at angle F or angle I, because I want to prove now angle side angle congruency, because I have a side and an angle set up. So I can prove angle side angle if I do these two side lengths. If I compare those two angle measures, angle G to angle J. Or I could also write out another possibility in purple here. If I were to compare these two angles using the same type of philosophy that they're alternate interior angles because of this transversal that's intersecting the parallel lines. If I go the purple route, in saying that angle F is congruent to angle I, then I would have angle side. So you have two options here, however you'd like to proceed in order to prove that these two triangles are congruent. You can either use angle side angle, or you could use angle side here. So I'm going to back out actually the purple and just go with the blue. But you could have just as easily done angle side, but let me do here angle side angle. So I'm going to say that because these lines are parallel, I can say that angle FGH has to be congruent to angle IJH. And that's because of the definition of alternate interior angles. And then lastly, I just need to prove those central angle measures. So I have angle GHF is congruent to JHI because of the definition of vertical angles. So now I have two angles and a side. So I have angle side angle. So I can say that these two triangles are congruent. So triangle FGH is congruent to triangle IJH because of angle side angle congruency postulate. Sorry we went over our time a little bit, but I wanted to make sure that we explained all of that completely. If you have any questions, then please post a comment below. Otherwise, thank you guys very much for signing in and watching my recording. I'm here for you every Monday, Wednesday, and Friday. Thursdays are writing sections and Tuesdays are reading sections, so please join me for those as well. If these videos are helpful to you, please like and subscribe to my channel. But otherwise, Dr. Todd, do you want to say goodbye to everybody? Come on, Dr. Todd, you guys say goodbye to everybody. You want a cookie? Oh, come on. Dr. Todd, come on, you guys say goodbye to everybody. Dr. Todd is very tired right now. Come on, you guys say goodbye. That's your job. Come on. Can you say bye? Can you say bye? Can you say bye? Good boy. Very good boy. Thank you guys very much for watching. I'll talk to you all on Friday.